Right, this is the Pearson Edexcel Further Pure Maths 2 FP2 paper from November 2021. I'm a bit worried about my voice, so we're just going to go straight into it with no small talk. Show that this thing is divisible by 66. So to be divisible by compound numbers like 66, you just need to be divisible by all its primes. 2 times 3, 3 times 11 makes 66, so we just need to be divisible by these things. Of course, to be divisible by 2, you just need to be even. This ends in a 0, so it's even, so that's good. To be divisible by 3, you need to have your digit sum be a multiple of 3. So just add all the digits, and if that's a multiple of 3, which in this case it is, then it's definitely divisible by 3, the original number. And now to be divisible by 11, you need to have an alternating sum that's divisible by 3. Or 0, I put in brackets, and I've done that because this one happens to be 0. Alternating sum just means plus, minus, plus, minus, plus, minus, of course. 0 counts as a multiple of 11. 0 would have counted here as well for a multiple of 3. As you know, that doesn't matter, does it? Because you can't get 0 and you just do some adding. Anyway, cool, so 0 counts here. So it's divisible by 11, it's divisible by all 3 of them, so therefore it's divisible by 66. That's what you need to do. The first thing I'll say about this one here is that I couldn't put this in PowerPoint very easily, so I've just decided to use blocks instead of stars, so you'll see what I mean in a second. Explain why this is closed. Closed just means that whatever inputs you put in here, the output is also a member of the group. This is the group of positive integers, including, I think, 0 here. It says, so positive integers and 0. Well, if we put in 2 positive integers, when you take away 2 positive integers, you get an integer. Now that integer could be negative, which would mean it would be out of the group, except the modulus ensures that it's either positive or 0, which is in the group. So anything that you do here will be, any answer will be in the group, it will be a positive or 0 integer. And so yeah, it will be in the group, so therefore it's closed under the operation. It doesn't create things that are outside of the group. Show that 0 is an identity. So okay, if we do m star 0, which I'm going to represent as a block here, because like I said, I couldn't do stars. M star 0 is m minus 0 modded, which is just m modded, which is m. You have to check it both ways. The hint that I use is this 2 marks here. Like this is clearly 1 mark, or worth of work. So put the 0 in front. You need to check both cases because, of course, you can't guarantee commutativity since it doesn't say that it is. So you do it the other way around and you still get m, and so therefore it's fine. 0 is an identity for any element m. Good. Show that elements have an inverse. So just choose itself. Usually it's itself or something quite obvious. But m star m minus m is 0, and 0 is the identity, so therefore m is its own inverse, and in fact all elements are their own inverse, which is good. And then determine if it forms a group. Now to do a group you need to have 4 things. Sorry, did I call this a group earlier? That was spoilers, I guess. We haven't shown it's a group yet. It's just yeah, sure. So let's now say that let's show that it's a group. Now you need 4 things. You need to be closed, which we've already shown that it is. You need to have an identity, which we've shown that it does. You need to have an inverse every element, which we've also shown that they do. And you also need to be associative. That's the last thing, which basically means when you take 3 elements or 3 things in the group, or a pseudo group thing that we're going to show as group. When you have 3 of them like this, you can do them in any order. You can do the last 2 and then combine with the first, or you can do the first 2 then combine with the last. Now, if you actually do this with algebra here, so we can say if we look at this left-hand side, n star p is this, and then m star that is going to be this, because it's just m minus this one all in a mod. Now, when you do it on the right-hand side, it looks a bit different. It ends up looking like this. These 2 things don't look like they're the same. Maybe they are, but actually, if we're going to aim for this not to be a group, all we really need to do is say, well, we just need 1 counterexample. So if we just choose m is 1, n is 2, p is 3, for example, and put it in here, 2 minus 3 is minus 1, modded is 1, 1 minus 1 is 0, modded is still 0. But over here, 1 minus 2 is minus 1, modded is 1, minus 3 is minus 2, modded is 2. And those 2 things aren't equal, so this isn't associative, which means it's not a group. So I was calling it a group earlier just because I'm tired, and I was assuming that it was the whole time. But I remember now it's actually not a group, because it's not associative, so it's not a group. Good. Question number 3 then talks about Euclidean algorithm. So, okay, let's do the Euclidean algorithm on 125 and 87. So 125, you don't have to write it like this. This is how the textbook writes it. It's not how I think of it in my head. I just take the bigger number, take away multiples of the smaller number until you get too small. So 125 take away 87 is 38. That's too small to take away another 87, so you just leave it as 38. Then you repeat the procedure with the number you were sort of taking away, and then the new number you got. So how many 38s can you take away from 87? Well, you can take away 2 of them before you get down to 11, which is too small to take another one away. So this is kind of the remainder. You can also think of it as in terms of division. You can say 87 divided by 38 goes twice with 11 left over. Anyway, the next one will be 38 equals 3 lots of 11 plus 5 remainder. So just take away 3 lots of 11 and then you get 5 left over, and then 11 is take away 2 lots of 5 and you have 1 left over, and when you get to 1, that's where you stop. And the reason you stop there is because you can actually just write this whole thing backwards and arrive here. So you can say 1 is 11 minus 2 lots of 5, like I was saying. And then 5 is 38 minus 3 lots of 11, so you put that in there, 38 minus 3 lots of 11. And what I'm going to do here is just some algebra without any algebra. So 1 lot of 11 minus 2 times minus 3 is plus 6. So it's 1 lot of 11 plus 6 lots of 11s makes 7 lot of 11s minus 2 lots of 38. And then 11, though, is 87 minus 2 lots of 38, so just replace that with 87 minus 2 lots of 38. 7 lots of 87 minus 14 lots of 38 minus 2 lots of 48 makes minus 16 lots of 38. And then one more time, right? 38 is 125 minus 1 lot of 87. Expand this out and we get this. And so I think this relates to here, right, because B is 23 and A is minus 16. And of course you can check this in a calculator. You can check it in a calculator as you're going along just to make sure you're not making any stupid mistakes. But yeah, write down a modulus, multiplicative inverse, of this mod 125. So you take this statement here, and if you just mod it 125, well, 125 times any whole number is 0 mod 125. So that just goes away, right? That just doesn't matter. 87 times, well, we've got it right here, 23 is therefore going to be 1 mod 125, and so the multiplicative inverse is 23, so that's quite cool. Solve the linear congruence. This, of course, we're going to use this, it's going to help us. We've got a 16 here, which isn't very helpful, but we have got an 87, and we just learnt that 23 times 87 is 1 mod 125, so let's just front multiply both of these by 23. And now this bit here, 23 times 87, is 1, so that just mods 125, so that just makes B here. These two things multiply to make this, and then this isn't one of the usual residue classes that you use. So just take away 125 a couple of times and you get down to there, and that would be the more usual answer to leave it as, and that will be our answer, which is cool. Okay, 4 is another question about groups. Group has all of this. Now this is a very big number that I don't think a calculator, maybe a calculator would tell me what this is, but I don't know. Use Fermat's little theorem. Okay, and determine which of these are possible subgroup orders. So we need a theorem here, which is that the order of a subgroup, you can only have a subgroup of order that's divisible of the original order of the group. So for example, if you've got a group with 8 elements, subgroups could only have 2 or 4 elements in there, or 1 if it's the trivial subgroup. It's got to divide 8, right? You can't have a group order 8 and then a subgroup order 5. Like, that doesn't work. And this is just a theorem that you can quote. I believe it's by this person. I actually don't know whether you have to quote his name. I should have looked that up. That is his name. I don't know whether you have to quote his name, but you can just quote this, that the order of theorem must divide the order of the group. So if you're saying that, or if the question is saying, is it possible for you to have a subgroup of order 11 elements in the group? What you just need to figure out is, does 11 divide this number here? If it does, then that's great. It can be. It's possible. If it doesn't, then it's definitely not possible. So okay, let's just work out what this is, mod 11. Because, of course, asking whether this divides this is just to say, is this 0 mod 11? Like, that's the same thing to say. So okay, this is where Fermat's little theorem comes in, because 11 is prime. And Fermat's little theorem says that any number to the power that prime minus 1 is congruent to 1 mod that prime. So 46 I'm just using because 46 is here. But it could be 8, it could be 10, like it could be any number here, as long as that's 1 less than this, and this is prime. So how do I use this then? Well, 46 to the power 46 is the same as this, right, I think? Because 10 plus 10 plus 10 plus 10 plus 6 is 46. But mod 11, all of these things are 1 because of Fermat's little theorem. So it's just 1 times 1 times 1 times 1 times 1 mod 11. Which of course is just this, mod 11. So I think I can just write this as this. And this one I'll do the same thing, right? You just have 7 left over instead of 6, because you can just use 47 here, that's fine, you still put a 10 here, and you just end up with 7 left over. Now, of course, 46 itself is congruent to 2 mod 11, because 46 is 44 plus 2. 44 is just 0 mod 11, so congruent to 2 mod 11, so I can replace that with a 2, and that, of course, with a 3. These numbers are small enough just to deal with now. 2 to the 6 we should know is 64. And now, I can't remember what I did here. What have I done? Okay, what I think I've done is 3 to the 4 times 3 to the 7. Now, 3 to the 4 is 81, because it's 9 squared times 9 squared. I'm sorry, because it's just 9 squared. Now, 81 is 4 mod 11, because 11 goes to 77, and there's 4 left over. So yeah, 3 to the 4 is just 4 mod 11, and then there's 3 to the 3 left over, which is 27. But 27 is just 5 mod 11, I guess. And then 4 times 5 is 20, and then add them together for 84. And then that's not 0 mod 11, that's 7 mod 11, right? Because you go from 77 to 84. So that's not divisible. This number is not divisible by 11, it leaves 7 left over. So that's not possible. And now we deal with 21. Now the problem with 21 is it's not prime, which means you can't use Fermat's little theorem, because Fermat's little theorem needed a prime to be here. Now I think what you're actually supposed to do was say that 27 is 3 times 7, and then, sorry, 21 is 3 times 7, and then use that because they're both prime. I didn't do that. What I said was 46 is 4 mod 21, because 21 goes to 42 and there's 4 left over. And 47 is obviously 5. So I got this. And then I just looked at the, like 5 squared is 4 mod 21. So you could break this down into like 5 squareds and just say they're all 4s. But actually, if you just look at the 21 times table, just find some numbers in here, maybe further down the line, that are really useful with powers of 4 and 5. And 4 you can actually write as 2, can't you? Because it's 2 squared to the 46, that's 2 to the 92 or whatever, I think. So, but looking at these numbers here, 126 strikes to me, because that means 5 cubed is minus 1 mod 21, because it's just 1 short of a multiple. So that seems quite useful, because that will break it down nicely. And also 63 seems like a very helpful number, because, or was it 63? Did I use 63? 2 to the 6 is 64. Yeah, 2 to the 6 is 64. So 2 to the 6 is 1 mod 21. And that seems really helpful, because, like I said, this can be 2 to the 92. And here I've broken this down a ton, haven't I? 3 times 15 is 45, plus another 2 is 47. And 5 to the 3 is minus 1, so I'll just replace that with minus 1. Although I'll apparently break this down first. I want 6's because they make 1 mod 21, so 6 times 15 is 90, plus another 2 is 92, and that's just a 1 there. 1 to the 13 is just 1, minus 1 to the 15 is minus 1, so this makes a minus 25. I've actually already realised that that's 4, so that's actually just a minus 4. 2 squared is 4, so there's 4 minus 4, which is 0, which means it is divisible by 21. So this is possible because this number is divisible by 21. So that's, there were lots of ways to do that bit, I'm sure. Lots of ways to make that work, but that was one of the ways, I guess. So, cool, a complex number question. You should basically be praying for a question like 5a here, even 5b as well, because you absolutely should have done this process to death. Z is x plus iy. You legit just shove that in here to get this. You then group the real and imaginary parts like this, and then you say, okay, well, the modulus of a complex number like a plus bi is the root of a squared plus b squared. And so therefore, if you square both sides, you get this. So if I square both sides of this, of course, square a product separately, so 4 squared times this thing squared. There's no expanding out to do here. This thing here, reading from this, is literally just this bit squared plus y squared, and there's no squaring out and there's no imaginary bits, because there aren't any here. So we get this. And then we can, of course, just expand everything out. I'm going to take a drink because this bit is just so trivial. You expand out and you do some stuff. I think you get this and this and this, and yeah, and that's nice. When you see this number, you know you've got it right, because radius is therefore just 4. Center is this with some minuses in there. Remember that you're actually talking about the complex plane here, so you have to go back to this bit, and yeah, you have to put it back into complex numbers rather than just writing brackets 0.6, 12.8. Put it back in a complex number. Radius is 4, and you'll have your answer. Next bit is a drawing bit. I just need to cough, so I'm going to put the mic out for a second. Hopefully that wasn't too bad, sorry. And yeah, so now drawing this, well, okay, here. We've figured out this is a circle. Now what this is actually talking about, z plus 9, well, you need to write that as z minus minus 9 first. And, okay, that means that the distance from z to minus 9 is over here. And the distance from z to minus 12i, sorry, to 12i, because there's just one minus here, 12i is up here. Now the distance, z is some complex point where the distance to 12i times by 4 is the distance to 9. So like you can imagine, this is the circle by the way, because it's just centre 0.6, 12.8, which is just a bit above here. Radius 4. So this point here, for instance, is on the circle because the distance to 12i looks like, if you times it by 4, is about the distance to minus 9. So that's where that circle comes from. And yeah, we want the distance to 9 to be less than 4 times the distance. So we want to be on the outside, right? Like here is a good point because the distance is less than 4 times the distance from there to there. So yeah, we want to be on the outside of the circle. But we also want this to be true. So let's write this as a more normal complex number. And this stands out because that's the same place as the center of the circle. So the center of the circle is there. This is directly below it. 4 below it, and 4 below it is great because the radius of the circle is 4. So it's on the circle here, immediately below 4 down. Now this is minus pi over 4 and pi over 4. So these are two lines going outwards like this. This is just core pure 1 maths, I think, isn't it? Two half lines going out, pi over 4 and minus pi over 4. All dashes because you can't be on them because there's strict signs here. And we want to be between those two lines. And we also want to be here. So that just leaves this area here, I think, as our answer. Right, let's see whether my voice can even do the rest of this. So we've got a recurrence relation here. It's a second order one, which is cool, proved by induction this. So it's second order, so we need two base cases. So we should go with 1 and 2, right, because those are the ones they've given us. So when n is 1, you just test whether this works. So you do u1 equals minus 3 to the 1 factorial, which is just minus 3, so that works, good. And then you try n is 2. So u2 is minus 3 to the 2 factorial. That's 9, that's 2, so that makes 18, which is also good. So we've got two base cases that work. So now we assume that for any n equals k, that uk equals this thing here. So we assume this with k, and then we just investigate uk plus 2, and we also assume uk plus 1 is this here, because we've got two base cases to work with, we can do this. So we assume both of these things, and then we investigate uk plus 2 by putting in this thing here for this, and this one here for that. So we do this, and now this looks messy, but I've just replaced the k's with n's, and then I've also, the n's with k's, and also this thing with this assumption, and this thing with this assumption. So that's there. And now let's just factorize. So looking at this, they both have a minus 3 to the k, so I'll leave 1 minus 3 behind here. They both have a k factorial, which means I'll leave behind a k plus 1 here, because that's the last term in this factorial. And I think I'm also going to factorize out a minus 3, and leave behind a minus 3 here, because minus 3 times minus 3 is 9. And then I'll just leave behind all of this from the first term. And from here, of course, this minus 3 is factorized out, so that just leaves behind a plus 1, I guess. This, I said, when I took the minus 3 to the k out, that leaves one of them behind. And when you take the k factorial out of this, that just leaves a k plus 1 behind. But now I notice actually there's a k plus 1 in common I can also factorize, so let's do that, and we get this. And now I can just expand this out. I've also put this minus 3 and this minus 3 to the k together to make this. And also, k factorial times k plus 1 is just k plus 1 factorial, isn't it? But here, you can just factorize out a minus 3. When you expand this out, you get this. Factorize out a minus 3, and then factorize the minus 3 out into here to get a k plus 2 there, and then this k plus 2 can become a k plus 2 factorial, or make that into a k plus 2 factorial, and you have this, which matches up perfectly, and then you give your usual spiel about how that shows that you're done, and you're done. So that's good. Question 7 is quite a long one then, so let's just do the first bit first. We have this integral to do with a reduction formula, it looks like. So, okay, we need to do an integral by parts first. That's how all these start, right? So you need to decide. I never do the dv v u du thing. I wasn't taught that. All I think of it as is you just have two functions here, one of which you want to integrate a couple of times, or once, and then put it here as well. And then one of them you want to leave alone and then differentiate, and you have a minus integral sign in the middle, and that's integration by parts, mate. Smashed it. So we need to decide which one of these two things we're going to integrate. Now, the obvious one to integrate is that one. However, when you look at the answer they want, you've got this to the power of 3 over 2. Right now, this thing is to the power of a half, because that's what a square root is. So it actually looks like they want me to integrate this one to make it a power of 3 over 2. So okay, I can do that, except to integrate this, it doesn't really work. Because when you think about differentiating objects like this, you have the differential of the thing inside matters, and the differential of this is 10t, that comes out to the front. So if you want to do reverse chain rule kind of stuff on this, you need a t in the front to cancel. But that's okay, because I've got loads of t's at the front. So let's split these t's to be tn minus 1 times t, and that gives me the t necessary to use reverse chain rule on this bit here. So okay, now I can do reverse chain rule on this red bit, and now, like I said, integration by parts. All you do is you integrate one of the two functions, so this one, put it here, integrated, and then you leave this one alone, and then differentiate it, and then there's a minus integral sign in the middle. That's just how integration by parts works in my head. And can we just verify that this integrates to this, or just differentiate this to check? Differentiate this, you get 3 over 2 at the front, cancel that nicely. This becomes a power of a half, which is the root, so that's good, and then differentiate this is 10t. 10t would cancel with a 10th just to make t, and good, so this differentiates that. So that works. This, of course, just differentiates this. That's trivial. So yeah, this is good. This works. Let's simplify that up. That becomes this. Now I've split this back out into 4 plus 5t squared to the power of a half, which is just the square root, times this to the power of 1, which makes 3 over 2. A half plus 1 is 3 over 2. And the reason I've done that is because also that n minus 1 is just a number. It looks weird, but it's just a number. It doesn't matter to the integral. So that just goes out to the front, and the 15 comes from here. Now, I can expand this out, right? I can do this times 4 plus this times 5t squared. The reason that's good is because t squared times tn minus 2 is just tn, because 2 plus this is just n. And that's great because when I have two things in an integral adding, I can just integrate separately. So I think I can write this as this. Following? So just this bit is just here, then you can just split this integral into two integrals, so that's good. Now this thing here, bring the 4 out and bring the 5 out, because those are just constants, so I'll just do that there. Bring the 4 out, bring the 5 out. This thing here is just in minus 2, because there's just a minus 2 there. And this thing here is just in, so we get this. 5 over 15 is a third. Add this to both sides and factorize out the in. And now this is 3 over 3 plus this, that's 3 plus n minus 1 is 2 plus n all over 3. And now I think I can just divide by, or times everything by 3 to make these 5s, which is good. And divide everything by n plus 2, which gives me those, and I think I have my exact answer. So that's cool. It's always good that you know what you're aiming for. That's very helpful. But yeah, that's the first part done. Second part is a bit different, and then it brings it all together in the third part. Second part is asking you to do a surface integral. Now, this is what the formula books say. This is a parametric one, so we use the parametric version. This is just from the book. So we need dt by dx, we need dx by dt. So dx by dt, 5 times this is just root 5, and then that becomes a 4. It wants that squared, so we'll square that. Root 5 squared is just 5, and then this squared is 8. Likewise here, dy by dt is just 2t cubed, square it for this. Put that into here, y itself there, replace that with that as well. So that's good. I'm going between 0 and 1 because that's what t is bounded between. So this is good. This is going to be the answer. Let's just tidy it up. So factorize out t to the 6 from in here. This root is a product, so I can just do the root separately to make this. This is great because that's just the thing that I want. This is t to the 3 times t to the 4 is t to the 8, t to the 7, sorry. And we have what was required there. So that's good. That's the first bit done. So that's our next 5 marks got done. I don't know why I've written that again. That's the same thing as there, so I don't need it. Good. So that's that there. And then it's saying, okay, now evaluate that. So now can we evaluate this? Now we need to use part A, of course. This is part A, saying this can be written like this. Now, okay, so this here, well, this is just pi lots of in, where n is 7. So, okay, 7 is clearly important here, but in, when n is 7, you just use this. So this is going to be pi times, and then all of this, where n is 7. So replace that with a 7, 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 and this will become I5. But I5 is just this with a 5 there, I think. So I think we get this. So okay, it's pi, there's just a pi there. times this here, ignoring the pi, is I7. But I7 is just this with some 7s here. And that makes that a 5, which is there. And I've just essentially just evaluated this and this to get these fractions here. But now I5, well, I5 is just this with 5s in here. So you just do it again. You just replace all these with 5s, keeping all this bit the same. Replace all these with 5s, and then that becomes an I3. And I3 is just the integral when there's a 3 there. Tidy all of that up, or do the actual substituting thing, and you get this. But I3 is getting deja vu, I guess. I3 is just this, but with 3s here. And then you finally get down to I1. And I1 is going to be helpful to you because I1 is actually just integrable. And we've actually already done it, right? We've actually integrated this. This is just reverse chain rule. So tidy all this up and get the numbers. But this here is just, we did that integral before. It's this. I know I could have simplified this, but I thought it was funnier to leave it on the screen as it is. So that's what I did. So anyway, this integrates this. We already saw that, and then put 1 in, put 0 in, and you get this, and you get that number there. And then you just type that into a calculator, and you get this answer. I don't know. I haven't actually done it. I just stole that from the mark scheme. Anyway, that's the entire question. I thought it was just a lovely question, really, really good question about reduction formulas. So yeah, moving on. So eigenvectors, nice. This is an eigenvector for A. That means this thing here, eigenvectors. If you haven't watched 3 Blue 1 Brown's video about eigenvectors and eigenvalues in his Essence of Linear Algebra course, I don't know what you're doing with your life, because you just need to watch it, and this will make a lot of sense when you watch it. I won't discuss it now because I can't be bothered, because he's done that in great detail and it's amazing. So literally just go watch that. Anyway, we have this, which means A times this vector here equals lambda times this vector here. And we just need to find lambda by comparing the top row maybe. So 5 times 2 minus 2 times 1 minus 5 times 2 is equal to 2 lambda. You can just solve that for lambda. And once you've got lambda as minus 1, you can just read the middle row. 0 times 2 plus 3 times 1 plus p times minus 2 is minus 1 times 1, because lambda is minus 1. And you get this, and you find p as 2, which is what they wanted. Good. And then it says determine the remaining eigenvalues. So eigenvalues are found by doing the determinant of a minus lambda I. So you just do all the diagonals minus the lambda, and then you find the determinant of this and set it to 0. So okay, the determinant of this is this times the matrix of this, the determinant of this matrix. So this times this minus this times this. So just to be clear, that's this one times this one minus this one times this one. And then you do minus this one times the determinant of these 4 at the ends. So this times this minus this times this, which is there, and then plus again this one times the determinant of these 4. So this times this with a minus. Just be super careful with all the negatives, like and the expanding. It takes a while, but you just have to be careful, and you're fine. And eventually you get this. At this point, check that lambda is minus 1 works, because you know lambda is minus 1 should work, and it does. So I know that I haven't made a mistake here. And now we just need to find the other 2 values. Now this is a cubic, but you have one solution, so it's not hard. Most people at this point would do polynomial division with lambda plus 1. I'm not going to, because I think it's just much easier to spot what the answer is. So essentially this cubic factorizes into this times something else, which is a quadratic. I can clearly see that this needs to be 1, because this times this makes this. And I can see clearly this needs to be a 6, because this times 6 would make that. If I just put an a here as a placeholder for a second, and then just investigate what the lambdas do. There's 1 lambda over here. Over here, there's a lambdas plus, how else am I getting lambdas? Plus 6 lambdas. So a lambdas plus 6 lambdas must equal 1. So we get this, and a is minus 5, and we have this, which factorizes this, and so our values are minus 1, which we already knew, 2 and 3. Those are our those aren't our eigenvectors. Those are our eigenvalues. Apologies for the typo, though. Those are the eigenvalues. Good, and so for the other 2, which are 2 and 3, find the eigenvectors. Let's start with 2. So we set up this equation again, but we know this should be a 2 here. Just use an x, y, and z for your unknown eigenvector. Expand this out, top row, middle row, bottom row. You get this, this, and this, which can tidy up into this, and this. Or this, take away 2 to get this, and then divide everything by 6 to get this. Now, there's a lot about matrices and stuff in Corporeal 1, and I think it's Corporeal 1 book, isn't it? You don't really have to go into a great deal about it, but essentially there isn't a unique solution to this. So what you do is you just make one up to start with. So you just say, okay, well, wouldn't it be nice looking at this equation if y was just 2? Because that would make z minus 1, and that's a nice number. And then if y is 2 and z is minus 1, just look at this equation here. Like, does it just work? Well, y minus z is 3, and then that means so x is 3, and then it also works here, which it will do because they're not linearly independent. So there's more complex stuff going on there, but in these questions, don't quote me on this because I'm not 100% sure it's right, but it seems like every one that I've ever done, you just pick one to start with, and the other two just always work when you do that, and just pick a nice sensible one to start with, and you shouldn't end up in too much trouble. But anyway, so the eigenvector is 3, 2, minus 1 for that one. And then you just deal with the eigenvector of 3, which is the other one we had, so you just do the same thing. I literally copied and pasted all of this, so I hope it's all correct. You get these. That's nice, because it just means z is 0. These two you can see are just linearly dependent on each other. Right, they're just multiples, which tells you there's no unique solution here, but x is 1 and y is 1 will be the easiest way to just make both of those work. And yeah, so the eigenvector is 1, 1, 0, and we'll have our other answer. Good, so write down, this is incredible typing work, write down a matrix P and diagonal D such as this. So P is just the matrix where you use the 3 eigenvectors in columns, the eigenvectors being that, that, and that. So that's that, and then D is just the diagonal matrix with the eigenvalues as the diagonals. Just make sure you use the right corresponding eigenvalues. So minus 1 made this vector, 2 made this vector, and 3 made this vector. So just use those in the right order. And then it starts going weird, the question. So this is just the final 6 marks of the paper here. It just asks you to solve a random differential equation. So okay, well, we can do that. U dot is du by dt, this is separable, this is all just corporeal 1 and 2, so they're just assuming that you know how to do this, which you should do because you'll have to do those books. So okay, times by dt divided by u, this makes log of u when you integrate both sides, this makes kt plus c, and then you can raise both sides to the power e. More usually you write this as e to the kt times e to the c. E to the c is just some constant a, and it's just a e to the kt, so that's usually how you write that. So okay, fine. Then it starts talking about all of this, which is just, it's a weird question, but it's the last question in the paper, so I guess that's why, right? It's just a weird question to ask. But anyway, so you have this. Well, okay, is this. So it starts talking about p's here. So if we replace a with that, then that seems sensible because they're about to make us use p inverses. So now at least I've got a p inverse in here. And now p inverse xyz, which is just this last bit here, they're telling us to just use UVW, so okay, let's just replace that with UVW, that bit there. Now, if I front multiply both of those by P inverse, I'll get this, because P inverse P just cancels. But P inverse x dot y dot z dot, they've asked me to write as this, so I can do that. The diagonal matrix is just the diagonal matrix we found earlier, which is this. And when you multiply that by a vector like this, you're just going to get minus u plus 2v plus 3w. I don't mean plus, so I just mean like this. And that's all great because now we've got u dot equals minus u, v dot equals 2v, w dot equals 3w, and this is where they just told us how to solve that, right? Or they didn't tell us, but we solved this. We solved this with k, and now we've just got various things as k. K is minus 1, means that this means, so okay, so u is here is just this with a minus 1 there. When k is 2, which is essentially what this is, you just put a 2 there, and you can make this number different just because it's a different equation, so it's going to have a different constant probably, maybe, could do. And then k is 3 means you just put 3 there, so that's cool. Now that's not quite the answer, because of course we're supposed to solve x, y, z, right, not u, v, w. But okay, that's when you just go back to here and you can front multiply this by p to get this. P times p inverses just goes away. But you know what p is. You worked out what p is. You wrote down what p was earlier. So now we can just do this. You could have also just done p inverse, but I didn't bother. You can now just do p times this. This is the vector UVW. You can just imagine vectors here. This times this is going to give you x, y, z. And then, of course, you just multiply this out and you get that. And that'll be the final bit in the paper. Yeah, thank you for watching. And yeah, I'll see you next time.